Tonight, we're going to dig into one of the strangest detective stories in the history of spaceflight. In 1977, two robotic explorers left Earth on what was supposed to be a short tour of the outer planets, a few years of work, and then silence. Instead, they're still alive today, still phoning home from a place no human instrument had ever reached before. And when they finally arrived at the true edge of our solar system, the place where the sun's influence gives way to the galaxy itself, almost nothing matched what we expected. The boundary sat in the wrong spot. Billions of miles past every calculation. The structure surrounding our sun turned out to be the wrong shape entirely. A bizarre magnetic corridor appeared that no physicist had ever theorized, and the empty blackness beyond turned out to be anything but empty, anything but quiet, anything but what the textbooks promised. 6 separate findings, each one forcing scientists back to the chalkboard. By the time we're done tonight, you'll understand exactly how a pair of machines built before the first home computer ever existed ended up redrawing the map of our cosmic neighborhood. If you enjoy this kind of deep dive into the mysteries hiding in plain sight above our heads, drop a like and subscribe. It genuinely helps more people find this channel. Let's get into it. It's 1977, and inside a clean room at Cape Canaveral, technicians are putting the finishing touches on 2 nearly identical robotic spacecraft. NASA has sold the public and Congress on a tidy 5-year mission. Fly past Jupiter, fly past Saturn, gather what data you can, and then let the spacecraft drift quietly into irrelevance as their power dwindles. Voyager 2 actually leaves the launch pad first, lifting off on August 20th. Voyager 1 follows about 2 weeks later on September 5th, but it's riding a quicker, more direct trajectory, which means it will actually arrive at Jupiter and Saturn ahead of its sibling. That's the strange little quirk behind the numbering. It has nothing to do with which one left the ground first, and everything to do with which one gets there first. Each spacecraft tips the scales at a little over 1,800 pounds and stands roughly as tall as a 1-story building. Bolted to each one is an array of cameras, spectrometers, magnetometers, and particle detectors, all aimed at unlocking the secrets of the 2 largest worlds in our solar system. But the mission planners had bigger ambitions hiding behind the official 5-year plan. They'd noticed something remarkable. The outer planets were about to line up in a configuration that only happens once every century and 3 quarters. If you time a launch correctly, you can use the gravity of each planet to fling your spacecraft toward the next one. Jupiter slingshotting you to Saturn, Saturn slingshotting you onward, and so on, all the way out to Uranus and Neptune. Try to do that trip without the alignment, and you'd need rockets and fuel budgets far beyond what existed at the time. NASA recognized the gift the planets were offering and built a mission, internally nicknamed the Grand Tour, to take advantage of it. Publicly, though, the agency kept its ambitions modest. Study Jupiter, study Saturn, then let nature take its course. Few people in 1977 seriously entertained the idea that either spacecraft would survive into the 2020s. Nobody expected the cameras to capture active volcanoes on a moon, or rings around a planet nobody thought had any, or oceans hiding under ice. And absolutely nobody expected that the most groundbreaking chapter of the mission would unfold decades later, far past the planets entirely, at a boundary scientists thought they already understood reasonably well. Here's what researchers believed about that boundary back when Voyager left the launch pad. They knew the sun isn't just a ball of light sitting quietly in the middle of the solar system. It's constantly exhaling a continuous stream of charged particles, mostly stripped down protons and electrons, pours off the sun in every direction at velocities in the hundreds of miles per second. Physicists call this outflow the solar wind, and it's not a gentle breeze. It's a plasma, a gas so energetic that its atoms have been torn apart into ions and free electrons. We can trace the discovery of this phenomenon back to a University of Chicago physicist named Eugene Parker, who in the late 1950s worked out the math showing that the sun's outer atmosphere, the corona, is simply too hot to stay gravitationally bound to the star. The gas has to escape continuously, not just during flares or storms. Parker's idea was met with real skepticism inside the scientific community at first. Some prominent physicists assumed any outward flow would only happen sporadically during periods of heightened solar activity. Then satellites went up in the early 1960s and settled the argument. The solar wind blows constantly, every single day, rain or shine. Busy sunspot sites cycle or quiet one. The sun sheds roughly 1 million tons of material every second through this process. That number sounds enormous until you remember the sun's total mass. Even bleeding off 1 million tons per second, it would take longer than the current age of the universe several times over to meaningfully dent its bulk. That outward streaming wind eventually runs into something. Space between the stars isn't a true vacuum. It's filled with an extremely sparse soup of gas and dust called the interstellar medium, something on the order of 1/10 of a particle in every cubic centimeter. To put that in perspective, the air you're breathing right now contains roughly 10,000 trillion times more particles per cubic centimeter. The space between stars is a far better vacuum than anything we can manufacture in a lab on Earth. And yet, sparse as it is, over distances measured in trillions of miles, that thin gas carries real pressure, real momentum, real mass. There's another wrinkle. The interstellar medium isn't stationary relative to us. Our entire solar system is in motion, orbiting the center of the Milky Way at roughly 450,000 miles per hour. From the sun's point of view, the galaxy's gas isn't sitting still waiting for the solar wind to arrive. It's rushing past like a headwind hitting a car windshield, where the outward push of the solar wind exactly balances the inward press of that galactic headwind. A boundary forms. Researchers name this boundary the heliopause, the literal edge of the sun's domain. Cross it, and you've left a region shaped by our star and entered a region shaped by the galaxy at large, governed by interstellar magnetic fields, populated by cosmic rays flung out from supernova across the Milky Way, rather than particles flung out from our own star. By the 1980s and into the 1990s, researchers had built increasingly elaborate computer simulations to model where exactly this boundary should sit and what shape it should take. These models incorporated magnetic field behavior, plasma dynamics, and the sun's motion relative to the surrounding gas. The consensus that emerged was fairly conservative. The heliopause should form something close to a sphere, maybe a touch stretched out on the side, trailing behind the sun's direction of travel, similar to the tail behind a comet, but nothing dramatic. Most models put the actual distance somewhere between 90 and 100 times the distance from Earth to the sun, what astronomers call an astronomical unit, or AU. That works out to roughly 8 to 9 billion miles. It seemed like a solid, defensible estimate given the data available at the time. Researchers had decent measurements of the solar wind strength near Earth, decent estimates of the interstellar medium's pressure from astronomical observations, and the underlying physics. The equations governing magnetized plasma had been well understood for decades. Run the numbers, and 90 to 100 astronomical units was where the math kept landing. Before reaching that ultimate boundary, the models predicted the solar wind would slam into an earlier feature called the termination shock. Here's the underlying physics. The solar wind travels faster than the speed at which pressure disturbances can propagate through the plasma itself, which makes it supersonic, similar conceptually to how a fighter jet outrunning the speed of sound produces a sonic boom. When supersonic flow meets resistance, in this case the slow pushback of the interstellar medium, a shock front formed. At that shock, models predicted the solar wind would abruptly decelerate from its blistering supersonic speed down to something far more sedate, compressing and heating up dramatically in the process, with particle density spiking several-fold. Calculations placed this shock somewhere around 75 to 90 astronomical units, a bit closer to the sun than the heliopause itself, with the exact distance fluctuating depending on how active the sun happened to be at any given moment. More solar activity pushes the shock outward, less activity lets it drift inward. Between that termination shock and the ultimate heliopause boundary, models predicted a turbulent transition zone called the heliosheath, solar wind material that's already been slowed and heated, now flowing outward and sideways as it tries to squeeze around the obstacle posed by the surrounding interstellar gas. Researchers expected this zone to be messy and turbulent, but still fundamentally solar in character, still made of particles that originated at our own star. Estimates put its thickness at somewhere between 10 and 20 astronomical units. And beyond the heliopause itself, models predicted would be the unfiltered galaxy, a sharp jump in galactic cosmic rays, the high-energy particles flung outward from supernova explosions and other violent events scattered across the Milky Way. These particles do penetrate into our solar system today, but the heliosphere acts as a partial shield, deflecting and slowing a meaningful fraction of them before they ever reach the inner planets. Past the heliopause, with that shielding gone, models predicted cosmic ray intensity should roughly double or triple. They also predicted the crossing itself should be reasonably crisp, taking perhaps a few weeks to a few months at most, with solar wind plasma dropping away, cosmic rays surging, and the magnetic field swinging around to a new orientation as the spacecraft traded the sun's field lines for the galaxies. Researchers were, by and large, confident in this picture. The underlying physics of shocks and magnetized plasma had been studied and refined across decades. The models might be off on the exact mileage. Sure, nobody expected pinpoint precision, but the broad strokes, a termination shock somewhere somewhere in the 75 to 90 astronomical unit range, a heliosheath roughly 10 to 20 astronomical units thick, a heliopause crossing around 90 to 100 astronomical units, a relatively clean transition into interstellar space. That basic architecture seemed solid. It wasn't, not even close in some respects, and the gap between prediction and reality turned out to be just the opening chapter of the surprises waiting at the edge of the solar system. To really appreciate what came next, it helps to understand exactly what kind of hardware was doing this work, because everything Voyager achieved, it achieved with engineering frozen in the early 1970s, before the personal computer existed, before the internet, before cell phones, before pocket calculators were even common. The onboard computing systems are almost comically modest by today's standards. Each spacecraft actually runs 3 separate computer subsystems working in tandem. One handles commands arriving from Earth, one processes and packages science data for transmission, and one manages the spacecraft's orientation and pointing. Combined, all 3 systems share something on the order of 70 kilobytes of memory. A single modern smartphone photograph takes up more storage than that. And yet engineers on the ground can still, even now, write and upload new software to these ancient machines. Back in the early 2000s, NASA engineers patched around a failing memory chip on one of the spacecraft entirely through remote software changes. More than a decade later, ground controllers successfully switched the other spacecraft over to a set of backup thrusters that had sat completely dormant for nearly 4 decades. And those thrusters fired exactly as designed. Picture trying to debug code written half a century ago, running on hardware you can never physically touch, where every single command you send takes the better part of a day just to arrive. Power comes from a trio of radioisotope thermoelectric generators on each spacecraft, compact units that exploit the natural radioactive decay of plutonium-238. As that plutonium decays, it generates heat, and a bank of thermocouples converts that heat directly into electricity. No moving parts, no fuel to run out in the traditional sense, just the slow, steady, unstoppable march of radioactive decay. At launch, each spacecraft's generators produce something close to 470 watts, but that output erodes year after year as the plutonium decays, dropping by roughly 4 watts annually. Decades on, the available power has dwindled to a small fraction of what it once was, forcing mission engineers into an ongoing, unending triage. Every instrument still running, every heater keeping delicate electronics from freezing solid, every watt of transmitter power, all of it draws from a steadily shrinking budget. The cameras were the first major casualty, switched off entirely back in 1990, once their planetary targets had all been visited. Other instruments have been powered down one by one in the years since. Eventually, inevitably, there simply won't be enough electricity left to run anything at all, and the spacecraft will go fully dark. Communication with these distant machines runs through NASA's Deep Space Network. 3 enormous radio dish complexes positioned roughly equidistant around the globe, in California, in Spain, and in Australia, arranged so that no matter how the Earth rotates, at least one dish always has a clear line of sight to wherever the spacecraft happen to be. Each of these dishes spans well over 200 feet across. A radio signal leaving the more distant of the 2 spacecraft takes upward of 22 hours just to reach Earth at the speed of light. Send a command and you wait the better part of a day for it to arrive. Then wait again for confirmation it was received and executed. A full round trip stretching past 40 hours for a single simple exchange. And by the time that signal completes its multi-billion-mile journey, it has faded to almost nothing. A whisper measured in quintillionths of a watt, among the faintest signals humans have ever managed to detect and decode from the depths of space. This, all of it, the kilobyte-scale memory, the slowly dying nuclear batteries, the whisper-thin radio signal, is the equipment that ended up rewriting our understanding of where the solar system actually ends. Keep that contrast in mind as we walk through what these aging machines found out there, because almost nothing about it matched the tidy predictions drawn up decades earlier. But before any of that, there were planets to visit, and the planetary leg of the mission alone would have justified the entire program, even if the spacecraft had died the moment they left Neptune behind. Jupiter came first. The faster traveling of the two spacecrafts swept past the giant planet in March of 1979, with its twin arriving a few months later in July. What both spacecraft sent back utterly transformed our understanding of the largest planet in the solar system. Take the Great Red Spot, a feature astronomers had been watching through telescopes for centuries without ever really understanding what it was or how it worked. Up-close imagery revealed it to be a colossal anticyclonic storm, rotating counterclockwise, towering several miles above the surrounding cloud deck, large enough to swallow more than one Earth inside its swirling boundary. Its reddish hue, scientists came to believe, comes from complex organic compounds cooked up when sunlight breaks apart simpler molecules in Jupiter's upper atmosphere. That storm wasn't alone. The spacecraft's cameras revealed dozens of smaller tempests scattered across Jupiter's banded cloud tops, pale ovals and dark, elongated streaks, each one individually larger than most hurricanes that ever form on Earth. All of them locked into a complicated dance, merging, splitting apart. The very first one ever confirmed anywhere beyond Earth. Far from being dead, Io turned out to be the single most volcanically active body anywhere in the solar system, with multiple eruptions caught in the act during the flybys alone. And later, surveys cataloging hundreds of distinct volcanic centers across its surface. The moon's surface gets constantly repaved by flows of molten sulfur and silicate rock, giving it its striking palette of yellows, oranges, and reds. While some eruption plumes were measured reaching well over 100 miles above the surface, hurling material outward at speeds exceeding 1,000 miles per hour. What powers all that violence? Not radioactive decay, the usual explanation for geological heat inside a planet, but tidal flexing. Jupiter's overwhelming gravity combined with the gravitational tug of neighboring moons repeatedly squeezes and stretches Io's interior as it orbits, generating tremendous friction and heat in the process, melting rock that then erupts at the surface. This was a mechanism theorists had proposed, but never actually confirmed until Io provided the proof, and it permanently changed how scientists think about what can power geological activity on a world. Not just the slow decay of radioactive elements deep inside a planet, but gravitational squeezing from a nearby giant. That same basic principle would later be invoked to explain activity on other icy moons, and it remains a live possibility for moons orbiting giant planets around other stars entirely. Europa offered a completely different kind of mystery. Its surface turned out to be smooth, icy, and crisscrossed with an intricate web of cracks and ridges, conspicuously short on impact craters, a strong hint that something keeps resurfacing it relatively recently in geological terms. Long, straight fractures called lineae stretched for hundreds of miles across the ice, while certain regions displayed a jumbled, chaotic texture, as if sheets of ice had broken apart and refrozen in a disordered jigsaw. The natural implication, one that has captivated planetary scientists for decades since, is that liquid water might be sloshing around beneath that icy shell, kept from freezing solid by the same kind of tidal heating driving Io's volcanism, just gentler. Voyager's instruments couldn't prove an ocean was actually down there. The case rested on circumstantial surface evidence and modeling, but the possibility was enough to make Europa one of the most tantalizing targets in the entire search for life beyond Earth, an obsession that later missions would deepen considerably by detecting magnetic signatures consistent with a salty, electrically conductive layer hiding under the ice. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury, displayed a patchwork surface, ancient, heavily cratered dark terrain sitting right alongside younger, brighter regions carved with parallel grooves and ridges, evidence of geological resurfacing at some point deep in its past. Callisto, the outermost of the four giants, presented the opposite story, a surface so thoroughly pockmarked with craters that it appears to have remained essentially frozen in time for billions of years, untouched by the kind of renewal evident on its neighbors. And then there was a discovery nobody had been specifically hunting for. Jupiter has rings, faint ones, composed of fine dust-sized particles, nothing remotely close to the dramatic ice rings encircling Saturn, but real nonetheless, confirmed for the first time during the 1979 flyby. Astronomers had floated the possibility before, but no Earth-based telescope had ever managed to detect them directly. Their existence hinted at something broader. Perhaps ring systems aren't some special rarity reserved for Saturn alone, but a relatively common feature among giant planets, sometimes spectacular, sometimes nearly invisible. By the time the spacecraft pulled away from Jupiter, they had already returned more raw data than every previous observation of the planet combined, going back centuries. Thousands of photographs, detailed magnetic field maps, radiation measurements, atmospheric composition readings, close-up data on 4 major moons and several smaller ones besides, plus the unexpected bonus of a previously unknown ring system. The mission had already paid for itself many times over, and Saturn was still waiting. The faster spacecraft reached Saturn in November of 1980, with its sibling trailing in behind it in August of 1981. People had been staring at Saturn's rings since Galileo first noticed something odd surrounding the planet back in the 1610s, though he famously misinterpreted what he was seeing, describing the planet as having handles or ears rather than a true ring. It took until the 1650s for Christian Huygens to correctly identify a flat ring encircling the planet. By the time Voyager launched, astronomers had already mapped out several broad ring divisions, with a sizable gap separating 2 of the major bands, but nobody had any real sense of just how intricate the structure actually was. Up close, each of those broad rings dissolved into thousands upon thousands of individual narrow ringlets, structure on a scale no Earth-based telescope could ever have resolved. Far from being solid sheets, the rings turned out to be made of countless individual chunks of ice and rock, ranging from particles smaller than a grain of sand all the way up to boulders the size of a house, each one independently orbiting the planet according to its own slice of orbital mechanics. The cameras caught waves rippling through the ring material, braided strands twisting around one another, dark radial markings that rotated along with the rings, and whose cause wasn't immediately obvious. Later attributed to fine dust particles temporarily lifted above the ring plane by electrostatic forces. Tiny moons orbiting right at the edges of certain rings turned out to be doing crucial gravitational housekeeping, herding stray particles back into line and keeping ring boundaries crisp rather than letting them diffuse outward over time. A pair of small satellites flanking one particularly narrow ring kept that ring's material tightly confined through their combined gravitational influence. And that ring itself displayed an odd braided structure, several strands appearing to wind around each other in a way unlike anything else observed in the rings, with later observations showing the braiding shift and change as the shepherding moons nudged the ring particles around over time. The overall picture that emerged was staggering in its complexity. Saturn's rings aren't simply a flat disk of leftover debris. They're a dynamic system, shaped continuously by gravity, orbital resonance, and constant low-speed collisions between particles, producing intricate structure at every scale, from features spanning thousands of miles down to the behavior of individual boulders just a few feet across. Density waves rippled outward through the rings. Compression patterns generated by gravitational resonances with various Saturnian moons, similar conceptually to sound waves traveling through air. Vertical bending waves warped sections of the ring plane up and down in response to other gravitational disturbances. And despite spanning many thousands of miles across, the rings themselves are astonishingly thin. In most places, only a few dozen feet from top to bottom, proportionally thinner than a sheet of paper relative to their width. Titan, Saturn's largest moon, had already been known to possess an honest-to-goodness atmosphere, the only moon in the solar system with one substantial enough to rival an actual planet's, a fact established decades earlier when a researcher detected the spectral signature of methane gas surrounding it. The faster spacecraft made a deliberately close pass, swooping within a couple thousand miles of the surface, a maneuver so demanding it locked that spacecraft out of ever visiting Uranus or Neptune afterward, which is precisely why the responsibility for the ice giants fell to its twin. The sacrifice turned out to be worth it. Titan's atmosphere proved even thicker than expected, with surface pressure roughly half again what we experience at sea level on Earth, denser than the atmosphere of any other moon or planet in the solar system, aside from Venus. Its composition turned out to be overwhelmingly nitrogen, much like our own atmosphere, laced with methane and a stew of other organic compounds: ethane, propane, acetylene, evidence of active and complex chemistry happening continuously in its hazy skies. A thick layer of orange smog completely obscured the surface from view. Photochemical haze generated as sunlight breaks methane molecules apart, leaving behind complex organic particles, similar in some ways to compounds that may have existed on the very early Earth. The cameras couldn't punch through to photograph the ground, but the other instruments returned a wealth of information: temperature, pressure, and composition readings at varying altitudes, painting a picture of a moon with something analogous to a complete weather cycle, just built around methane instead of water. Methane evaporates, forms clouds, falls back down as rain, almost certainly pooling somewhere on the surface into lakes or seas of liquid hydrocarbons fed by rivers and streams of the stuff. Surface temperature hovers around 290 degrees below 0 Fahrenheit, cold enough to keep water locked up as rock-hard ice, yet still warm enough for methane to exist comfortably as a liquid. That combination made Titan an instant priority target for future exploration, one that a later orbiter mission and an accompanying surface probe would eventually deliver on, descending through the haze to reveal a landscape carved by flowing liquid, dotted with lakes, river channels, and dunes built from organic sand grains. With Saturn behind them, the two spacecraft's paths diverged for good. One was sent climbing above the plane of the solar system, prioritizing speed toward interstellar space over any further planetary encounters, its days of visiting new worlds finished. The other pressed onward toward Uranus, the only spacecraft ever to visit that strange, sideways tilted planet, and remains so to this day. That encounter came in January of 1986. Uranus turned out to be tipped over on its side by roughly 98 degrees relative to its orbital plane, meaning it essentially rolls along its orbit like a barrel rather than spinning upright like a top, a configuration that gives each pole an uninterrupted 42-year stretch of daylight, followed by 42 years of darkness over the course of the planet's 84-year journey around the sun. The flyby revealed an atmosphere that was, frankly, a bit anticlimactic visually: pale blue-green from methane-absorbing red light, with relatively few visible cloud features, though winds were still clocked at speeds exceeding 500 miles per hour. 10 previously unknown moons turned up in the imagery, along with 2 additional rings, beyond the handful already known from ground-based observation. The real showstopper at Uranus was a small moon called Miranda. Its surface displayed an almost schizophrenic geology, regions of ancient, heavily battered terrain sitting directly adjacent to oddly grooved patches striped with parallel ridges and valleys, plus towering cliffs, one estimated at several miles high, dwarfing the tallest canyon walls found on Mars. The overall impression was of a world that had been shattered apart and then haphazardly reassembled, different terrain types jumbled together with no clean transition between them. One theory holds that a massive ancient impact actually broke Miranda apart entirely, with the fragments later drawing back together under their own gravity into the patchwork moon observed today. Another invokes tidal heating, though Miranda's current orbit doesn't generate nearly enough stress to explain it, suggesting its orbit may once have looked very different. The true cause remains an open question, but something dramatic clearly happened to that small moon at some point in its history. The final planetary encounter came at Neptune in August of 1989, a flyby representing the true culmination of the whole Grand Tour concept, occurring a full 12 years after launch, with the spacecraft having successfully threaded its way past all 4 giant planets in sequence. Scientists had largely expected Neptune to resemble a slightly bluer, equally bland version of Uranus. Instead, it displayed the most dynamic, turbulent atmosphere of any planet visited during the entire mission. A massive dark storm system roughly the size of Earth churned in its southern hemisphere, broadly analogous to Jupiter's famous red storm. A small, fast-moving bright cloud feature, quickly nicknamed for its speed, circled the planet in well under a day, and wind speeds reached upward of 1,300 miles per hour, the fastest sustained winds ever measured on any planet in the solar system, an almost absurd figure for a world receiving so little sunlight and warmth that far from the sun. Neptune's largest moon delivered its own jolt. It orbits the planet backward, in the opposite direction from the planet's own rotation, an arrangement essentially unheard of for a large moon, and a strong indication that it wasn't born alongside Neptune at all, but was instead captured later, likely originating from the distant icy debris field beyond Neptune's orbit. Despite a surface temperature hovering close to 390 degrees below 0 Fahrenheit, among the coldest measured anywhere in the solar system, the moon turned out to be geologically active, with geysers of nitrogen gas erupting from beneath its surface. The leading explanation involves seasonal solar heating. Even at that immense distance, sunlight can still warm dark patches beneath a translucent layer of frozen nitrogen, causing the nitrogen to sublimate directly from solid to gas, building up pressure until it eventually ruptures through the surface and vents into space, carrying dark streaks of material that settle back down nearby. With Neptune in the rearview mirror, the planetary phase of the mission was officially complete. Both spacecraft had blown past their original mandate many times over. Active volcanism on a moon of Jupiter, tantalizing hints of a hidden ocean on another, an unexpected ring system around the solar system's largest planet, tens of thousands of individual ringlets at Saturn, a thick organic chemistry-rich atmosphere on Titan, a shattered and reassembled moon at Uranus, ferocious winds and active geysers at Neptune. And both spacecraft were still very much alive, still returning clean data, still capable of doing real science. So NASA made the call to keep going. The mission would now formally extend into what became known as the interstellar phase, chasing down the boundary where the sun's authority finally runs out. No machine built by human hands had ever traveled far enough to test that boundary directly. Scientists had their models, their careful predictions. Almost every one of them would turn out to be wrong. The faster of the two spacecraft reached the termination shock on December 16, 2004, registering a distance of 94 astronomical units from the sun, somewhere around 8.7 billion miles. Remember, the models had predicted this shock would show up somewhere between 75 and 90 astronomical units. The spacecraft was already well past the outer edge of that range before it even got there. The termination shock marks the spot where the solar wind, still traveling faster than the speed at which pressure waves can move through the surrounding plasma, abruptly slams into the slower-moving resistance of the outer heliosphere and is forced to decelerate. It's a genuine physical boundary, a place where the plasma compresses and heats almost instantly. And the spacecraft had just found it considerably farther from home than anyone had calculated. What's stranger still is that the crossing wasn't a single clean event. The instruments first registered shock-like signatures back in August of 2002, around 85 astronomical units. Then oddly, those signatures faded. The boundary itself appeared to retreat outward over the following months, and the spacecraft found itself sitting back in ordinary, still supersonic solar wind, as though it had crossed prematurely and then uncrossed. The pattern repeated again the following year, the shock washing back over the spacecraft's position before retreating once more. It wasn't until December of 2004 that the spacecraft finally settled into the slower, denser, hotter plasma on the far side and stayed there for good. This back-and-forth breathing motion turns out to be driven by solar activity. When the sun is in an energetic mood, kicking out extra material and pressure, that added push shoves the termination shock farther outward. When solar activity eases off, the shock contracts back inward. The boundary isn't a fixed line drawn on a map. It's something closer to a slowly inflating and deflating balloon, responding to conditions back at the sun with a lag measured in months. The second spacecraft crossed its own termination shock on August 30th, 2007, at a distance of 84 astronomical units, roughly 7.8 billion miles out. And here's where things get genuinely puzzling. That's about 10 astronomical units closer to the sun than where its twin had crossed years earlier. If the boundary were a simple sphere, both spacecraft, traveling in somewhat different directions, should have crossed at roughly comparable distances. They didn't, not even close. This was the first solid piece of evidence that the entire structure surrounding our solar system isn't symmetric at all. It's compressed in some directions and stretched out in others. One spacecraft happened to be heading more or less toward the nose of the heliosphere, the direction facing into the sun's motion through the galaxy, a region that gets squeezed the way a bow wave compresses in front of a moving boat. The other was heading more toward the flank, where the structure has more room to relax outward. Researchers had floated this possibility theoretically before, but now they finally had hard measurements backing it up. Once past the termination shock, both spacecraft entered the turbulent transition region known as the heliosheath, expected to be a relatively straightforward zone. Slowed and compressed solar wind plasma still flowing generally outward, mixed with sideways currents as it tried to flow around the obstacle posed by the surrounding interstellar gas. Models predicted this region would take somewhere between 5 and 10 years to cross, with a thickness of roughly 10 to 20 astronomical units, putting the actual heliopause crossing somewhere around 2015, at a distance of perhaps 100 to 110 astronomical units. Then, starting around 2010, the data started doing something nobody had anticipated. The leading spacecraft began registering a steady climb in galactic cosmic ray intensity, the high-energy particles flung out from distant supernovae across the galaxy. Under the standard model, that intensity should jump sharply right at the heliopause itself, not gradually ramp up while the spacecraft was still clearly sitting in the middle of the helioheath. At the same time, the intensity of lower energy particles that originate at the sun was slowly declining. Particles that, according to the textbook picture, should vanish abruptly at the boundary, not fade out gradually beforehand. The spacecraft's other instruments still showed clear evidence of solar wind plasma. The magnetic field still carried the unmistakable signature of the sun's own field. So what exactly was going on? The answer arrived in June of 2012, when the instruments detected something genuinely unprecedented. A region where the magnetic field lines had snapped into near-perfect radial alignment, pointing straight outward from the sun, rather than the usual twisted, spiraled configuration imposed by solar rotation. And riding along those newly straightened field lines, particles were flowing in both directions simultaneously, solar particles streaming outward, galactic cosmic rays streaming inward. The field lines were behaving like an open highway, connecting the heliosheath directly to interstellar space. Researchers quickly dubbed it the magnetic highway. Nothing in any existing model had predicted a structure like this could even exist. The best working theory holds that the sun's magnetic field lines were actually reconnecting directly with the galaxy's magnetic field lines in this region, merging in a way that opened a free channel for particles to flow both directions at once. Essentially, a bridge spanning two regions that were otherwise supposed to be cleanly separated. The spacecraft spent roughly 2 months sampling this bizarre corridor. Cosmic ray levels climbed higher here than anywhere else measured in the Helios sheath, while solar particle counts dropped lower. In effect, the spacecraft was getting an early preview of interstellar conditions, sampling a region with a direct pipeline to galactic space, even though it technically hadn't crossed the true heliopause yet. Then, on August 25th, 2012, everything shifted again, and sharply this time. Solar wind particles all but disappeared. Cosmic ray counts jumped up to a new, steady, elevated plateau. The transition played out over just a handful of days, but oddly, the magnetic field direction itself didn't rotate the way the textbook said it should. It kept pointing in essentially the same direction it had throughout the Helios sheath. That single detail touched off real confusion and genuine scientific debate. Some researchers argued the vanishing solar particles and surging cosmic rays were unmistakable proof the spacecraft had finally crossed into true interstellar space. Others pointed to the unchanged magnetic field direction as evidence it hadn't, suggesting maybe there was some intermediate region nobody had anticipated. Maybe the boundary had layers nobody had modeled. The argument played out in the scientific literature for well over a year. Finally, in September of 2013, NASA made it official. The spacecraft had crossed the heliopause back in August of 2012 at a distance of 121 astronomical units, roughly 11.2 billion miles from the Sun. That's nowhere near the predicted 90 to 100 astronomical units range. It's 20 to 30% farther out, an overshoot of well over 2 billion miles compared to what the models had promised. This was the first genuinely shocking discovery to come out of the interstellar crossing. The heliopause simply isn't where decades of careful modeling said it would be, and the discrepancy isn't a rounding error. It's billions of miles. That gap implies either the solar wind is pushing harder than anyone had assumed, or the surrounding interstellar medium is pressing back with less force than estimated, or quite possibly some combination of both. Later analysis leaned toward the conclusion that the local interstellar medium is somewhat less dense than earlier estimates suggested. Not dramatically so, but enough to shift the equilibrium point outward by that 20 to 30% margin. The consequences of that ripple outward in interesting directions, because the heliosphere functions as a shield against galactic cosmic rays reaching the inner solar system. A larger than expected heliosphere implies somewhat better shielding than previously assumed, which in turn could have subtle effects on cosmic ray exposure at Earth across very long timescales, potentially touching atmospheric chemistry, even mutation rates, in ways scientists are still working through. The distance wasn't the only thing wrong. Researchers had also expected the heliosphere to be more or less spherical, perhaps somewhat elongated on the trailing side into something like a comet's tail, but fundamentally, a tidy, balanced bubble. What the data actually painted was a far stranger shape, something closer to a blunt bullet or an elongated teardrop. The leading face, the side getting hit by the headwind as the sun barrels through the surrounding gas, gets compressed into a flattened, blunted nose. The flanks get squeezed inward as well, and the trailing side stretches out behind for a distance that could plausibly run into the hundreds of astronomical units, far longer than anything on the leading edge. The first spacecraft had crossed near that compressed nose region at 121 astronomical units. Its twin crossed on November 5th, 2018, registering a distance of 119 astronomical units, a remarkably close match in raw distance, despite heading toward a different part of the boundary, more toward the flank rather than straight into the nose. That near agreement in distance, despite the very different approach angles, tells researchers the heliosphere isn't dramatically lopsided around its equator the way a true comet tail shape might suggest. The asymmetry is present, but more subtle than that, driven primarily by the compression happening directly ahead of the sun's direction of travel through the galaxy at roughly 450,000 miles per hour. Outside the heliopause itself, theory predicts there should be a genuine bow shock forming in the surrounding interstellar gas, conceptually similar to the wave that piles up in front of a boat's hull, somewhere in the neighborhood of 140 to 230 astronomical units according to the models. But given how badly those same models missed the heliopause's actual location, that estimate has to be treated with real skepticism. Neither spacecraft has reached it yet, so for now, it remains a prediction waiting to be tested. The overall shape carries real consequences for how easily cosmic rays from the rest of the galaxy can penetrate into our solar system. A perfectly spherical heliosphere would, in principle, offer roughly uniform shielding from every direction. A bullet-shaped one almost certainly doesn't, potentially leaving easier inroads for cosmic rays approaching from certain angles, perhaps especially from behind, through that long, stretched-out tail. The shape also isn't fixed for all time. Our sun is currently passing through a relatively small, somewhat denser patch of interstellar gas, sometimes called the local interstellar cloud, only a handful of light years across. The exact boundaries and density of that cloud help determine how compressed the heliosphere currently is. Many thousands of years from now, the sun will drift entirely out of this cloud into a different patch of the galaxy, with different ambient pressure, and the heliosphere will reshape itself accordingly. What the two spacecraft measured is best understood as a single snapshot, valid for this particular moment in a very long, very slow process. Whatever comes after us will likely find a heliosphere shaped somewhat differently. That's shocking discovery number 2. Not only is the boundary billions of miles farther out than predicted, its actual shape bears only a loose resemblance to the simple, symmetric bubble that decades of modeling had confidently sketched out. There was a third surprise wrapped up in all of this, separate from distance and separate from shape: the actual character of the transition itself. The models had predicted something clean, a boundary you could cross in a matter of weeks, or, at the outside, a couple of months, with solar plasma dropping away, cosmic rays surging, and the magnetic field swinging around to a new orientation, all in a tidy, well-defined sequence. What actually happened took years, not weeks. Starting back in 2010, cosmic ray counts began a slow, gradual climb, even while the spacecraft was still unambiguously parked deep inside the Helios heath, still detecting solar wind plasma on a regular basis. Then came the unexpected magnetic highway in 2012, that strange corridor of radially aligned field lines, allowing particles to stream both directions simultaneously, a structure nobody had theorized could exist at all. Then the sudden vanishing of solar particles and jump in cosmic rays on August 25th, 2012, complicated immediately by the fact that the magnetic field stubbornly refused to rotate the way the textbooks demanded, touching off more than a year of genuine scientific disagreement about whether the crossing had actually happened yet. Eventually, researchers worked out the resolution to that particular puzzle. The local galactic magnetic field, purely by chance, happens to run roughly parallel to the sun's own field direction in this particular patch of the boundary. A coincidence of geometry, nothing more. Crossing the heliopause here simply doesn't produce a dramatic compass needle swing, because both sides of the boundary happen to be pointing in roughly the same direction already. The second spacecraft's crossing played out quite differently. It happened far faster, over the course of roughly a single day, on November 5th, 2018. And this time, the magnetic field direction did shift. A modest rotation of around 20 degrees. Not a dramatic flip, but a clear, measurable change. Why the discrepancy between the two crossings? Simple geometry. The two spacecraft crossed the boundary in genuinely different locations. The boundary clearly isn't uniform in its structure from one spot to the next. Near the compressed nose region where the first spacecraft crossed, the boundary may be thicker, more layered, more prone to producing strange structures like the magnetic highway. Out toward the flank, where the second spacecraft crossed, the transition appears to be sharper, faster, with different magnetic geometry altogether. Both spacecraft also picked up something else after their respective crossings. The boundary doesn't just sit still once you're past it. The first spacecraft briefly detected solar particles reappearing in August of 2013, nearly a full year after its official crossing, before they faded away again for good. The boundary had apparently washed back over the spacecraft's position temporarily, then retreated once more, all without the spacecraft itself moving an inch. These oscillations trace back to solar activity, specifically strong bursts of solar wind that ripple outward through the heliosphere over the course of months, eventually reaching the heliopause and giving it a temporary outward shove, pushing the boundary past a spacecraft's fixed position before it relaxes back once the pulse dissipates. A solar storm in 1 year might not reach the boundary and produce a noticeable bump until a year or two later. None of this dynamic, breathing behavior had been built into the standard models, which generally treated the heliopause as something that drifts slowly over multi-year timescales, tied to the broader solar activity cycle, not something capable of oscillating back and forth over a period of mere months. Certainly not enough to wash back and forth across a stationary spacecraft's position without that spacecraft going anywhere. The unavoidable conclusion is that the edge of the solar system isn't a fixed line you could draw on a map and call settled. It moves, sometimes by several astronomical units over surprisingly short stretches of time. Ask whether a particular spot, 120 astronomical units from the sun, counts as solar system or interstellar space. And the honest answer depends entirely on when you happen to be asking. Today, it might read as interstellar. Next month, once a pressure pulse from an old solar storm finally arrives, it might briefly read as heliosheath again. A few months after that, it could swing back the other way. That's shocking discovery. Number 3, the crossing itself turned out to be a prolonged, messy, genuinely dynamic process, full of false starts, unexpected structures like the magnetic highway, and lingering oscillations, nothing resembling the crisp, well-behaved boundary the models had promised. Once safely on the far side, the leading spacecraft became the very first human-made object to directly sample true interstellar space, sticking its instruments straight into material that had never originated anywhere near our sun. Up to that point, everything humanity knew about interstellar space had come from indirect remote methods, spectroscopy of distant starlight, radio observations of hydrogen clouds scattered through the galaxy, theoretical extrapolation. Now, for the first time, there was a direct, in-place measurement. The particle density out there came in around 0.08 particles per cubic centimeter. For comparison, the best vacuum chambers humans can build on Earth still manage to contain around 1 million particles per cubic centimeter. Interstellar space, in other words, is a noticeably better vacuum than anything achievable in our most advanced laboratories. Though vacuum doesn't quite mean nothing. Not when you're talking about distances measured in trillions of miles. A single cubic meter of sea level air on Earth contains roughly 10 million trillion particles. Interstellar space out there carries something like 10 trillion times fewer particles per equivalent volume. Sparse almost beyond imagining, and yet, undeniably, not zero. The temperature readings came back surprisingly high, tens of thousands of degrees Fahrenheit. That sounds like it should be scorching, but temperature in this context measures the average kinetic energy of individual particles, not how much actual heat energy is available to transfer. With so vanishingly few particles around to carry that energy, there's essentially nothing there to burn anything. An astronaut somehow stranded in interstellar space would freeze solid almost instantly. Not roast, because there simply aren't enough particles bouncing around to transfer meaningful heat into a human body. Pressure measurements came in at an almost unimaginably tiny fraction of Earth's sea level atmospheric pressure, something on the order of 100 trillionth. And yet, tenuous as it is, that pressure is precisely what balances against the outward push of the solar wind at the heliopause, holding the whole boundary in equilibrium. Even an almost non-existent pressure multiplied across a boundary spanning many billions of miles adds up to something capable of stopping the sun's outflow cold. The spacecraft's plasma wave instrument also picked up something genuinely useful: oscillation events, ripples of compression and rarefaction traveling through the interstellar plasma, detected in bursts during 2012 and 2013. By measuring the frequency of these oscillations, researchers could back-calculate the electron density of the surrounding medium directly, an elegant trick that doesn't require waiting for a chance encounter with stray particles. Different oscillation events yielded slightly different density readings, varying by something like 10 to 20% across a span of just a few astronomical units. Evidence that the interstellar medium isn't perfectly uniform, even on relatively local scales. Denser pockets push harder against the heliosphere from whichever direction they happen to sit, while thinner patches let the boundary relax outward a bit more. The interstellar medium also carries its own magnetic field woven into the broader structure of the galaxy. The trailing spacecraft measured a field strength around 50 nanotesla out there. Compare that to Earth's surface magnetic field, which clocks in around 50,000 nanotesla, meaning the ambient galactic field is roughly a millionth the strength of our own planets. Faint as that sounds, over distances spanning light years, even a field that weak exerts real influence, shaping how plasma flows, accelerating cosmic ray particles, linking star systems together across the galaxy into a loose, sprawling web of interconnected field lines. None of these specific values, the density, the temperature, the pressure, the field strength, match the model predictions with any real precision. The broad categories were right. The actual numbers were consistently off in one direction or another. Each individual measurement forced another round of refinement, another update to existing models. That's shocking discovery number 4. The first direct measurements of true interstellar space revealed density, temperature, pressure, and magnetic properties that all diverged from the predictions. Not by enormous margins in every case, but consistently enough to matter. One of the strangest individual findings to come out of this whole interstellar phase involves something researchers started calling tsunami waves, genuine shock waves rippling through the interstellar medium itself, traceable directly back to outbursts from our own sun. When the sun produces a particularly forceful eruption, a coronal mass ejection, or an especially strong gust of solar wind, that disturbance travels outward through the entire heliosphere. By the time it reaches the heliopause, it arrives with enough force to slam into the boundary like a hammer blow, and that impact launches an actual shock wave outward into the surrounding interstellar gas. These waves crawl along at the local speed of sound in that thin plasma, far slower than the solar wind itself moves, but still fast enough to cover several astronomical units over the course of a year. The leading spacecraft picked up its first such tsunami in October and November of 2012. The plasma wave instrument registering sustained oscillations lasting several weeks, with the characteristic frequency allowing researchers to calculate the surrounding electron density at that moment. A second wave rolled through in April and May of 2013, showing a slightly different frequency, implying the local density had shifted somewhat in the interim. A third arrived in 2014. A fourth, the year after that. Each individual wave could be traced back to a specific solar outburst that had occurred years earlier, the disturbance racing outward through the heliosphere at supersonic speed, striking the heliopause and launching a fresh shock wave into the surrounding interstellar gas, which then took additional months or years to physically reach wherever the spacecraft happened to be sitting at the time. This revealed something nobody had fully appreciated before. The sun's influence doesn't actually stop dead at the heliopause. It's true that solar wind plasma itself, the literal material streaming off the sun, is confined within the heliosphere. But pressure disturbances, genuine shock waves, evidently propagate well beyond that boundary, rippling outward through interstellar space itself, possibly carrying for tens of astronomical units before finally dissipating as their energy spreads across an ever-widening front. These detections also helped settle the earlier debate about whether the heliopause crossing had genuinely occurred. The tsunami waves were clearly arriving from the direction of the sun, propagating through plasma with properties matching interstellar space rather than heliosheath material. If the spacecraft had still been sitting inside the heliosheath, it would have detected the original solar wind pulses directly, not secondary shock waves rippling through an entirely different medium on the far side of the boundary. Nobody had predicted this particular phenomenon at all. Researchers already understood that supernova explosions could generate genuine shock waves traveling through interstellar gas. That part of the physics was old news, but a shock wave generated by something as comparatively gentle as an ordinary solar storm, detectable by an instrument sitting billions of miles beyond the edge of the solar system, that came as a complete surprise. That's shocking discovery number 5. Pressure waves triggered by activity at our own sun keep rippling outward through interstellar space itself. Evidence that the sun's reach extends meaningfully farther than the heliopause boundary that supposedly marks its limit. Perhaps the single most puzzling finding to come out of the entire interstellar phase concerns the orientation of the magnetic field on the far side of the boundary. Heading into the crossing, models had predicted the galactic magnetic field should be tilted at a noticeably different angle compared to the sun's own field, which runs broadly radial but gets twisted into a loose spiral by the sun's rotation. The galaxy's field, by contrast, was expected to align roughly with the structure of the spiral arm our solar system currently sits within. Crossing the heliopause should, in principle, register as some meaningful rotation in field direction, not necessarily a dramatic flip, but a clear, detectable shift, marking the handoff from a field shaped by our star to one shaped by the broader galaxy. The leading spacecraft detected essentially no such shift. The field direction measured immediately after the crossing looked almost identical to what it had measured beforehand. That single, unassuming data point fueled months of confusion and debate among researchers trying to make sense of it. Eventually, the consensus settled on coincidence. In this particular patch of sky, the local galactic field just happens to run roughly parallel to the heliosphere's own field direction at the point where the spacecraft crossed. An accident of geometry rather than evidence. The crossing hadn't actually happened. The trailing spacecraft's crossing told a slightly different story, registering a modest field rotation of around 20 degrees. Not dramatic, but unmistakably real, and unmistakably different from what its twin had found at a separate crossing point more than 100 astronomical units away. That difference tells researchers something important. The magnetic field out in nearby interstellar space isn't uniform, the way a simple bar magnet model might suggest. It's structured, twisted, shaped by local plasma currents and the gravitational and magnetic influence of nearby stars. We now have direct measurements from 2 separate points, separated by more than 100 astronomical units, and they don't agree. Extrapolating confidently to other directions, other distances, simply isn't possible yet, with only 2 data points in hand. This matters because magnetic field orientation has a direct bearing on cosmic ray behavior. Charged particles don't travel in straight lines through space. They spiral along magnetic field lines as they move, with those field lines acting almost like channels guiding their overall path. A favorably oriented local field can funnel cosmic rays toward the heliosphere. An unfavorably oriented one can deflect them away instead. Understanding the actual structure of the local galactic field, rather than assuming some simplified textbook version, turns out to be essential for understanding how much cosmic radiation actually reaches Earth. That radiation exposure carries real downstream consequences. Cosmic rays influence atmospheric chemistry, contribute to the production of certain isotopes used in dating ancient materials, may play some role in cloud formation, and represent a genuine radiation hazard for any future astronauts venturing beyond Earth's protective magnetic field. Across geological timescales, the cosmic ray flux reaching our planet has clearly varied. Evidence preserved in isotope records locked away in ice cores and ocean sediment. Some of that variation traces back to changes in Earth's own magnetic field over time. Some likely traces back to nearby supernova events happening at various points in the galaxy's history. And some portion may well trace back to changes in heliosphere shielding as the sun drifts through regions of varying interstellar pressure and varying magnetic field orientation over the very long term. What the two spacecraft captured amounts to a single snapshot of the current configuration, not some permanent, unchanging arrangement. It will keep shifting as the sun continues its slow journey through the galaxy. That's shocking discovery number 6. The orientation of the magnetic field beyond the solar system caught researchers off guard, and what little data exists already shows real variation between 2 points only modestly far apart on a galactic scale. Closely tied to that magnetic field puzzle is one more wrinkle worth mentioning: where exactly the cosmic rays themselves seem to be coming from. Galactic cosmic rays are overwhelmingly protons, accelerated to tremendous energies by supernova shock fronts, by pulsar winds, by other violent processes scattered across the Milky Way, carrying energies that in some cases exceed what humanity's largest particle accelerators can achieve here on Earth. Both spacecraft carry instruments designed to measure cosmic ray intensity and rough composition, part of a broader effort to understand exactly how much shielding the heliosphere provides against this galactic radiation. As the leading spacecraft worked its way through the Helios heath, cosmic ray intensity climbed steadily, which made intuitive sense. The deeper into the outer heliosphere, the weaker the shielding, the more galactic radiation gets through. But the directionality of that radiation turned out to be lopsided in ways nobody had anticipated. Researchers had generally assumed roughly even intensity arriving from every direction. Instead, the data showed clear enhancement from some directions and a noticeable deficit from others. After crossing the heliopause entirely, cosmic ray intensity jumped to a new, higher plateau, roughly 10 to 20% above Helios heath levels. Solid confirmation that even the outer fringes of the heliosphere, billions of miles from the sun, still provide meaningful shielding against the unfiltered galaxy. But again, the directional pattern stayed lopsided, rather than smoothing out into something even. The trailing spacecraft confirmed the same basic pattern after its own crossing: elevated cosmic ray intensity in true interstellar space relative to the Helios heath, with persistent directional unevenness. That unevenness hints at real structure in the local interstellar neighborhood, perhaps nearby remnants of ancient supernovae, perhaps the galactic magnetic field itself channeling cosmic rays preferentially from certain angles while deflecting them from others. Curiously, both spacecraft registered somewhat lower cosmic ray intensity arriving specifically from the direction of the galactic center, which seems backward at first glance, since that's the direction with the highest concentration of stars and the most frequent supernova activity, exactly where you'd expect the most cosmic rays to originate. One possible explanation involves the galactic magnetic field being considerably stronger toward the galaxy's interior, effectively trapping and scattering cosmic rays attempting to propagate outward from that direction, so that fewer of them ever make it all the way out to our comparatively quiet corner of the galaxy. This remains an active area of ongoing research. Two spacecraft, sampling two locations, simply can't fully map out a three-dimensional structure spanning the entire sky. Future missions traveling in other directions entirely will be needed to fill in the rest of the picture, but the basic finding stands on its own. Cosmic rays out beyond the heliopause arrive from unexpected directions and unexpected proportions, and the simple, uniform from everywhere model that researchers had defaulted to simply doesn't match reality. Taken together, these findings paint a portrait of a boundary far stranger and far more dynamic than anyone walking into the project back in 1977 could possibly have anticipated. A heliopause sitting billions of miles farther out than predicted. A heliosphere shaped less like a simple bubble and more like a blunt-nosed bullet trailing a long tail behind it. A transition zone that stretched across years rather than weeks, complete with a completely unforeseen magnetic corridor connecting solar and interstellar space. An interstellar medium with measurable density, temperature, pressure, and magnetic properties all diverging from the predictions. Shock waves from solar storms rippling outward through supposedly empty interstellar space. A galactic magnetic field oriented in ways that varied noticeably even between two crossing points only modestly far apart. And cosmic rays arriving from directions the simplest models never anticipated. Every single piece of that picture had to be rebuilt, in some cases from scratch, once actual measurements finally replaced decades of careful but ultimately incomplete theorizing. All of this carries enormous weight for anyone seriously thinking about what an actual interstellar mission would require, because these two aging spacecraft have given humanity its first direct, ground truth measurements of the environment any future probe would have to cross. And the picture that emerges is sobering, to put it mildly. After nearly 50 years of continuous travel, the leading spacecraft has covered something like 159 astronomical units, roughly 14.8 billion miles. That sounds like an enormous achievement, and it is. But stack it against the distance to even the nearest star, and the scale of the challenge becomes obvious. Proxima Centauri, our closest stellar neighbor, sits about 4.24 light-years away, somewhere in the neighborhood of 268,000 astronomical units, on the order of 25 trillion miles. At the velocity this spacecraft is currently traveling, the trip would take something like 73,000 years, longer than the entire span of recorded human history, longer than agriculture has existed, longer than the time elapsed since the last ice age came to an end. And that spacecraft isn't even pointed toward Proxima Centauri. It's heading off in an entirely different direction. Roughly 40,000 years from now, it will make its closest approach to a different star entirely. Though close is relative. The distance at that closest approach will still be measured in well over a light year, meaning the spacecraft will simply drift past in the vast emptiness separating star systems, never actually entering whatever planetary system that star might host. Its twin, heading toward a different star altogether, will make a similarly distant pass at roughly the same point in the far future. These timescales expose the fundamental obstacle facing any realistic interstellar ambitions. The distances involved are so staggering that even traveling at tens of thousands of miles per hour amounts to barely crawling. Making interstellar travel remotely practical on human timescales would require velocities dramatically higher, at minimum a few percent of the speed of light, and realistically, something closer to 10% for travel times that don't span dozens of generations. 10% of light speed works out to something like 67 million miles per hour, more than 1,000 times faster than either spacecraft is currently managing. At that velocity, reaching Proxima Centauri would take around 42 years, still the better part of a human lifetime, but at least with continuous travel, and the cumulative dose becomes genuinely significant, demanding serious shielding for any human crew. radiation-hardened electronics throughout, and careful protective measures for any biological materials carried along for the ride. The baseline radiation environment the spacecraft measured gives future mission designers an actual number to engineer around, rather than a guess. Magnetic field measurements matter here too. Charged particle trajectories bend in response to magnetic fields, and even though the ambient galactic field out there is extraordinarily weak, on the order of a millionth the strength of Earth's own surface field, that weak field still has measurable effects over sufficiently vast distances. Proposed propulsion concepts that would use a magnetic sail to interact with the surrounding interstellar medium for braking or steering would need accurate field strength and orientation data to function as designed. And these two spacecraft have provided the very first direct measurements anyone has ever obtained. The tsunami wave detections add yet another wrinkle. Interstellar space evidently isn't calm and undisturbed the way many assumed. Shock waves triggered by our own sun's outbursts ripple outward across billions of miles. Other stars almost certainly generate comparable disturbances of their own. Any future interstellar probe might well encounter shock waves originating from a completely different star's activity somewhere along its multi-decade journey. Transient pulses capable of temporarily boosting local density or temperature, possibly elevating cosmic ray intensity briefly as well. Understanding that interstellar space is a genuinely dynamic, occasionally turbulent environment rather than a static, unchanging void matters enormously for planning any mission expected to operate for decades on end. The shape and scale of the heliosphere itself factor into mission planning too. Any spacecraft setting out from our solar system has to physically cross the heliopause at some point, and depending on the exact direction chosen, that crossing might happen anywhere from roughly 120 astronomical units out to potentially well beyond 150 astronomical units, or farther still if the chosen heading points toward the long trailing tail rather than the compressed nose. Knowing approximately how far a spacecraft needs to travel before it even reaches genuinely unfiltered interstellar conditions matters a great deal for mission design, and the heliopause also marks the practical limit of meaningful solar influence. Past it, a spacecraft is genuinely on its own. Communication delays only get worse from there. At 120 astronomical units, a one-way signal already takes the better part of a day. Push out to 1,000 astronomical units, and that climbs to several days each direction. Reach an actual light year, and you're waiting more than a year just for a signal to arrive one way. Then there's the Oort cloud to contend with, a theorized shell of icy debris believed to surround the entire solar system, beginning somewhere around 2,000 astronomical units, and potentially extending all the way out to 100,000 astronomical units, roughly halfway to the nearest star. The leading spacecraft won't even reach the cloud's presumed inner edge for something like 300 more years, and won't clear its outer boundary for upward of 30,000 years beyond that. Any genuine interstellar mission, even one traveling vastly faster than these aging probes, would spend the overwhelming majority of its journey still technically within the sun's own gravitational sphere of influence, passing through a region whose actual conditions remain almost entirely unknown. Is the object density out there high enough to pose a real collision hazard for a fast-moving spacecraft? Are there enough loose dust grains scattered around to cause damage at high relative velocity? These two spacecraft won't answer those questions. Their instruments will have long since gone silent before they ever get anywhere near that region. But the simple fact that 50 years of continuous travel still hasn't gotten either one there offers some real perspective. The solar system is bigger, by a wide margin, than casual intuition suggests, and the journey to truly open interstellar space is correspondingly longer than most people imagine. None of this rules out interstellar travel as a long-term goal. It does mean the challenge is sobering, rather than trivial. Propulsion systems capable of reaching a meaningful fraction of light speed. Structural materials robust enough to withstand decades of micro-impacts and accumulated radiation damage. Power systems that can keep functioning without maintenance for the better part of a century or more. Communication systems capable of bridging light years, and navigation systems that have to operate autonomously, since round-trip communication delays make any kind of real-time control from Earth completely impossible. What these two spacecraft have effectively done is hand future engineers an actual map of what they're up against. Real measurements of the environment any interstellar mission would have to survive, rather than a set of untested theoretical assumptions. Perhaps the most valuable lesson buried in all of this is something more philosophical. It's genuinely possible to build something, send it past the edge of the known solar system, and have it keep functioning for decades on end. The redundancy, the deliberate simplicity, the conservative engineering baked into these spacecraft from the start. That's exactly what allowed them to keep operating so far past their original design lifetime. Any future interstellar mission will need that same philosophy of robustness, just scaled up considerably further. If these spacecraft can keep running for 50 years, a genuine interstellar probe might need to keep running for 100 or more. If these spacecraft can still communicate from 15 billion miles away, an interstellar probe will eventually need to communicate across distances measured in trillions of miles. The challenges stack up fast. But these two machines have already proven the basic premise. Something built by human hands really can survive and keep working out there. At least for a very long while. Back on February 14th, 1990, with the leading spacecraft already about 3.7 billion miles from home, roughly 40 astronomical units past Neptune's orbit, and still many decades from the heliopause itself, NASA commanded it to swivel its camera platform around and look back the way it had come. One final glance homeward before the cameras were shut down for good to conserve dwindling power. The result was a sequence of images capturing the solar system from outside, a family portrait showing 6 planets caught in the same frame: Earth, Venus, Jupiter, Saturn, Uranus, and Neptune. Mercury was lost in the sun's glare. Mars was too small and dim to register clearly, and Pluto was simply too faint to pick up at all. In one of those frames, Earth appears as nothing more than a single pale point of light, smaller than a pixel, caught hanging inside a stray, scattered beam of sunlight. Carl Sagan, who had championed including cameras on the spacecraft in the first place, and who had also helped assemble the golden records writing along with them, saw that image and was moved to write some of the most widely quoted reflections ever penned about humanity's place in the cosmos. He pointed out that every human being who has ever lived has lived out their entire existence on that single speck of dust suspended in a sunbeam. Every war, every act of love, every triumph, every catastrophe, the entire sweep of human history played out on a mote barely visible from the edge of its own solar system. That image connects directly to everything the spacecraft would go on to discover years and decades later out at the true boundary of the solar system. The very same machine that captured that humbling photograph eventually crossed the heliopause, sampled true interstellar space directly, and measured the galaxy beyond the reach of our own star. From out there, genuinely beyond the sun's domain, Earth becomes even less significant by comparison. Just one small planet orbiting one ordinary star among the hundreds of billions scattered across the Milky Way, with the entire heliosphere itself amounting to little more than a modest bubble lost in the surrounding vastness. Everything these spacecraft uncovered out at the edge underscores just how much remains genuinely unknown, even concerning a boundary sitting comparatively close by in galactic terms. If careful decades-long modeling could still be off by billions of miles on something this nearby, how much more remains to be discovered farther out, across the rest of the galaxy, across the rest of the universe entirely? That single faint pixel of an image serves as a useful reminder of scale, how small this all is, how recent humanity's presence has been on any meaningful cosmic timescale. Earth itself runs on the order of 4.5 billion years old. Human beings have existed for perhaps 300,000 of those years. Organized civilization stretches back maybe 10,000 years. Spaceflight itself is barely 70 years old. These two spacecraft have been traveling for nearly 50 of those years, the better part of a human lifetime. And they've barely cleared the outermost edge of the solar system, just now settled into the earliest fringes of interstellar space. Even traveling at their current velocity, the nearest star remains tens of thousands of years away. The closest approaches either spacecraft will ever make to another star. Still many light years off in real terms, despite being labeled their nearest pass, lie tens of thousands of years in the future. Genuine interstellar travel, actually visiting another star system, exploring another planet orbiting a different sun, remains decisively beyond anything humanity is currently capable of. These spacecraft are interstellar only in the narrow technical sense that they've physically exited the heliosphere. They're drifting through the space between stars now, but they're not traveling toward any particular star. They're simply adrift. And yet, what they've already accomplished remains extraordinary by any reasonable measure. Two machines, built with technology that predates the personal computer, have traveled farther from home than anything else humanity has ever constructed. They visited worlds that had never before been seen up close. They crossed a boundary no human-made object had ever reached. They measured conditions that had, until that point, existed only as theoretical predictions in scientific papers. They demonstrated, repeatedly, that the universe holds more complexity than our best models can fully anticipate, that there are always more surprises waiting just past the edge of current understanding, that genuine exploration routinely uncovers questions nobody even knew to ask in the first place. That backward-glancing family portrait captures exactly that spirit, looking homeward one last time before turning fully outward toward the unknown, carrying forward into the dark. As of 2026, nearly 50 years removed from launch, both spacecraft remain technically operational, an almost absurd achievement, given they were originally engineered for a 5-year mission, 10 times their intended design life and counting. As a direct consequence, and certain instruments have already frozen solid and stopped returning usable data as a result. Back in 2020, engineers made the deliberate choice to shut off the heater, protecting one particular instrument on the trailing spacecraft, expecting that instrument to fail almost immediately once it dropped to roughly 74 degrees below 0 Fahrenheit, a temperature far outside anything its 1970s era design was ever meant to tolerate. Remarkably, it kept right on working anyway. Decades-old hardware operating dramatically below its intended thermal range and still faithfully returning data. But that kind of resilience can't last forever. Sometime around the middle to late 2020s, there simply won't be enough power left to keep both core spacecraft systems and any remaining science instruments running simultaneously, forcing engineers to start permanently powering down instruments one after another, rather than just temporarily. By somewhere around 2030, perhaps stretching to 2032 at the very outside, the power budget is expected to finally run dry altogether. At that point, there won't be enough electricity left to operate the transmitters at all. The signal will simply stop. The spacecraft will keep moving, fully intact. Antenna and solar panels and power generators all still physically attached, but entirely dead, with no way left to communicate anything back to Earth, drifting onward in complete silence. And they'll keep drifting essentially forever after that. The leading spacecraft is currently headed in the general direction of a constellation that, in roughly 40,000 years, will bring it within about 1.6 light-years of a particular star, the closest stellar approach anywhere in its foreseeable future, a distance that still works out to something like 9.4 trillion miles, nowhere near close enough to actually enter that star's planetary system, even if one exists there. The trailing spacecraft is headed toward a different patch of sky entirely, set to pass within roughly 1.7 light years of a different star on a similar multi-millennia timescale. After those distant flybys, both spacecraft will simply keep wandering the galaxy indefinitely, occasionally nudged by the gravity of stars they happen to pass relatively near over the course of millions of years, eventually settling into their own long, slow orbits around the center of the Milky Way, alongside every other star and stellar remnant out there, completing one full galactic circuit roughly every couple hundred million years. The golden records each spacecraft carries will remain physically attached the entire time. Gold simply doesn't corrode in the vacuum of space. No oxygen present to oxidize it. No moisture to degrade it chemically. Those disks should, by most estimates, remain intact and theoretically readable for hundreds of millions of years, possibly longer still. The odds that any civilization, anywhere, ever actually stumbles across either one are vanishingly close to zero. Space is simply too vast. The spacecraft themselves are far too small and far too dark to detect except at extremely close range, and neither one is even aimed at any specific star system in particular. But they'll be out there nonetheless, humanity's first true ambassadors to interstellar space, carrying a physical message from a species that may well no longer exist in any recognizable form by the time either spacecraft completes even a single full orbit around the galaxy. So what exactly is riding along on these golden records? Each one is a 12-inch gold-plated copper disc, deliberately engineered to survive for billions of years, floating in the vacuum of space. Gold resists corrosion and oxidation almost completely, and since there's no oxygen or moisture out there to begin with, the metal simply doesn't degrade the way it would sitting on a shelf on Earth. The actual content isn't stored magnetically or digitally in any conventional sense. It's physically etched directly into the surface as grooves, conceptually similar to an old analog vinyl record, except instead of carrying music from start to finish, these grooves carry a carefully curated cross-section of sounds, images, and music meant to represent Earth as a whole. Even if every electronic system aboard the spacecraft eventually fails completely, even after the power runs out entirely, the record itself will remain physically intact and, in principle, readable, assuming whoever eventually finds it has equipment capable of playing it back. The sounds chosen for inclusion were meant to capture something of Earth's sheer diversity. Natural sounds open the collection: wind moving through trees, rainfall, rolling thunder, surf breaking against a shoreline, a volcanic eruption rumbling and cracking, the deep, low-frequency groan of an earthquake shifting the ground. Then come the sounds of life itself, the haunting, complex songs of humpback whales, calls capable of carrying for hundreds of miles underwater, a chorus of birdsong drawn from multiple species, crickets chirping, frogs croaking from some unseen pond, a dog barking somewhere nearby. Distinctly human sounds follow, a newborn baby crying, that universal signal of new life beginning, footsteps, laughter, recorded from both men and women, a steady human heartbeat, the rhythm underlying every human life, the soft sound of a kiss shared between a parent and child, then the sounds of human tools and technology at work, a hammer striking metal on an anvil, a saw rasping through timber, a tractor engine idling, sounds of transportation spanning the ages, a horse pulling a cart, a steam train's whistle, a jet engine roaring overhead, and finally, the thunderous launch of a rocket, the very technology that propelled these golden records into space in the first place. Then comes the music, easily the most difficult and contested part of the entire selection process. How exactly do you choose a handful of recordings meant to stand in for the entirety of human musical achievement? Spanning every culture and every era, the committee responsible for assembling the record leaned on certain pillars of Western classical composition: intricate Baroque counterpoint, a towering symphonic masterpiece, an intimate string quartet, operatic drama, and a piece of revolutionary, almost primal orchestral writing that had scandalized audiences at its premiere decades earlier. But the committee understood from the start that Western classical music alone couldn't possibly stand in for the whole of humanity. So the final selection also reached for intricate percussive orchestral music from Indonesia, complex, interlocking rhythmic traditions from West Africa, ancient vocal traditions from Central African forest communities, some of the oldest continuously practiced song traditions belonging to Aboriginal Australian culture, the haunting sound of panpipes echoing through the Andes, the spare, meditative tones of Japanese bamboo flute music, the distinctive pentatonic structures running through traditional Chinese music, the elaborate melodic and rhythmic systems underlying Indian classical music, the raw emotional weight of American blues, the improvisational brilliance of early American jazz, the driving rhythm and storytelling of early rock and roll, and the dense, layered vocal harmonies of traditional Georgian choral singing. Every single inclusion meant leaving out countless, equally worthy alternatives, and that tension produced real disagreement within the selection committee. Debates over whether to lean more heavily into contemporary popular music, whether sacred and religious music deserved a place, and if so, whose religious tradition should be represented without seeming to slight every other one left out. In the end, the committee tried to strike some kind of balance between cultural breadth and what they judged to be lasting artistic significance, fully aware that any such list would inevitably overrepresent some traditions and underrepresent others, no matter how carefully it was assembled. Alongside the sounds and music, the record carries spoken greetings recorded in 55 different languages, ranging from ancient tongues no longer spoken anywhere on Earth, all the way through to major modern languages spoken by hundreds of millions or even billions of people today. Each greeting runs only a few sentences, but the underlying sentiment repeats again and again across every language included. A message of peace, of friendship, of hope that humanity might someday resolve its own internal conflicts well enough to join some broader community of civilizations out among the stars. It's a strikingly hopeful message, coming from a species that, even as the records were being assembled, remained deeply mired in war and division of its own. Beyond the audio content, the record also carries 116 still images, encoded not as conventional pictures, but as audio signals that can, with the right equipment, be converted back into visual form. Brightness values translated into a sequence of tones, representing each row of pixels in turn. The selected images run a wide gamut: basic mathematical and scientific diagrams explaining number systems, units of measurement, the structure of the atom, the double helix structure of DNA, the layout of our own solar system, a photograph of Earth seen from space. Landscapes follow: mountains, deserts, forests, oceans, meant to convey something of the planet's physical diversity. Diagrams illustrating human anatomy and reproduction made the cut too, a choice that sparked real debate within the committee at the time. Some members worried the content was too explicit. Others insisted any sufficiently advanced civilization encountering the record would need accurate information about human biology regardless of any discomfort. Photographs of people from a range of cultures, ages, and everyday activities round out the collection. Families sharing meals, children at play, athletes in motion, people working at various trades, architectural landmarks drawn from multiple civilizations, traditional and modern dwellings side by side, art and sculpture meant to showcase human creativity, and finally, a handful of images depicting modern technology and infrastructure, including, perhaps pointedly, a crowded traffic jam, a small acknowledgement of humanity's less flattering tendencies alongside its achievements. Putting all of this together amounted to a genuinely enormous collaborative undertaking, drawing on scientists, visual artists, professional musicians, linguists, and anthropologists, all working under serious time pressure, since the planetary alignment driving the launch schedule simply wasn't going to wait around for a more leisurely selection process. Technical limitations constrained every choice as well. The physical groove space available on a single disc placed a hard ceiling on total audio duration, meaning every minute devoted to one recording was a minute taken away from something else. Image resolution had to be weighed against the sheer number of images included, since cramming in more pictures necessarily meant lower fidelity for each individual one. Every single decision involved some kind of trade-off, and every inclusion meant something else. Something arguably just as worthy had to be left out entirely. In the end, the golden record amounts to something well beyond a straightforward scientific instrument. It's closer to a deliberate philosophical statement, a genuine, sincere attempt to answer an almost impossible question. What does it actually mean to be human? And what, out of the nearly infinite range of human experience, deserves to be preserved and presented to some hypothetical intelligence that knows absolutely nothing about us? The team that assembled it understood from the outset just how astronomically unlikely it was that the record would ever actually be found by anyone. The galaxy alone contains hundreds of billions of stars, and the space separating them is almost incomprehensibly vast. The odds that either spacecraft will ever pass close enough to another star system to even be noticed, let alone physically recovered, sit somewhere close enough to zero to be functionally indistinguishable from it. And even granting some improbable close pass, the additional odds that an advanced, technologically capable civilization happens to exist there at precisely the right moment in time stack the unlikelihood even higher. Most stars, as far as we currently understand, don't host planets capable of supporting life as we understand it. Most life, presumably, never evolves anything resembling intelligence. Most intelligent life, if it exists at all, may never develop the kind of technology necessary to detect, intercept, and physically retrieve a small drifting object from interstellar space. The record is, frankly, considerably more likely to eventually be destroyed than ever discovered, whether through an eventual collision with some stray object or simple accumulated radiation damage stretched out across truly geological timescales. But the actual value of having created it never really depended on the odds of discovery in the first place. The value lay in the exercise itself, in the disciplined, deliberate act of sitting down and asking what genuinely matters, what's truly worth preserving, what transcends any single culture or moment in time. The record stands today as a snapshot of Earth as it existed in 1977. A handful of the languages included have since gone extinct or fallen into severe decline. Some of the specific musical traditions represented are barely performed anymore. Certain images depict scenes or technologies that no longer exist in quite the same form. But it functions as a genuine time capsule regardless. A message sealed inside a bottle and cast adrift on a truly cosmic ocean. A simple, lasting declaration that a species existed here, that it thought and felt and built culture and dared to dream about what might lie beyond its own small world. The entire program, from initial development all the way through the Neptune flyby, carried a total price tag of roughly $865 million. A figure that, adjusted across the intervening decades, represents a genuinely remarkable return on investment, given everything it ultimately delivered. 4 giant planets explored in close detail, dozens of moons studied or discovered outright for the first time, the very first confirmed observation of active volcanism anywhere beyond Earth, the first real hints that an icy moon might be hiding a liquid ocean beneath its frozen shell, the first direct measurements of the termination shock, the first confirmed crossing of the heliopause itself, the first direct, in-place sampling of true interstellar space. Practically every modern textbook covering the outer solar system leans heavily on imagery and data gathered during these flybys. Every contemporary model attempting to describe the heliosphere incorporates the hard data these spacecraft sent back. Every serious conversation about the nature of interstellar space inevitably circles back to what these 2 machines actually measured out there. In a very real sense, this mission rewrote the working understanding of both the solar system itself and the boundary marking its outer edge. The discoveries kept cascading outward in their implications, well beyond the immediate findings themselves. Confirming that Eo's volcanism is driven by tidal heating fundamentally broadened how scientists think about possible energy sources for geological activity elsewhere, expanding the picture beyond simple radioactive decay deep inside a planet's interior to include gravitational flexing from nearby massive bodies, a mechanism now considered seriously relevant not just for other icy moons within our own solar system, but potentially for moons orbiting giant planets around entirely different stars as well. The tantalizing suggestion of a hidden ocean beneath Europa's icy crust kicked off decades of dedicated mission planning that continues right up to the present day, with later missions specifically designed to search that hidden ocean for any signs of biological activity, if life were ever confirmed to exist there. Independent of life on Earth, it would represent powerful evidence that biology can emerge more than once, even under conditions radically different from our own planets. The intricate structure uncovered within Saturn's rings, thousands of individual ringlets, shepherding moons, resonance-driven waves, turn that ring system into something close to a natural laboratory for studying orbital mechanics and disk dynamics more broadly, with the underlying principles later applied to understanding how planets form within the swirling disks surrounding young stars, how material accumulates into accretion disks around black holes, and even how entire galaxies maintain their broad disk-shaped structure. The flybys of Uranus and Neptune remain, to this day, the only close-up visits either ice giant has ever received from any spacecraft, meaning essentially everything currently known about their atmospheres, their magnetic fields, and their respective moon systems traces directly back to those brief, single passes. And then, of course, came everything discovered afterward, well past the planets entirely, crossing the termination shock, working through the turbulent helios heath, stumbling onto the entirely unanticipated magnetic highway, finally crossing the heliopause and pushing out into true interstellar space. The actual distance to that boundary turned out to be considerably farther than predicted. Its shape turned out to be lopsided, rather than the simple symmetric bubble everyone had expected. The properties of the interstellar medium itself diverged meaningfully from earlier estimates. Shock waves triggered by solar storms turned out to keep rippling outward through that medium, long after leaving the heliosphere behind. The galactic magnetic field's orientation caught researchers genuinely off guard, and the directional pattern of incoming cosmic rays revealed structure in the local interstellar environment that nobody had previously mapped. Every single one of these findings sent scientists back to revise their models, reconsider their underlying assumptions, and rebuild their understanding from a more accurate foundation. That, fundamentally, is the entire point of exploration. Not simply confirming what was already believed, but uncovering the gaps in that belief, finding the genuine surprises, learning over and over that reality consistently turns out to be more intricate and more interesting than any theory built in advance of actually going and looking. NASA has, for some years now, been quietly developing concepts for a genuine follow-up mission, something often referred to informally as an interstellar probe, though it remains firmly in the conceptual planning stage, with no confirmed launch date and no secured funding as of yet. The underlying scientific goals, though, are already fairly well defined. Directly answer the questions these two aging spacecraft raised but couldn't fully resolve on their own. A purpose-built interstellar probe would be engineered from the ground up specifically for this kind of extended journey, carrying more onboard power, a longer operational lifespan, more capable and sensitive instruments, and considerably higher cruising velocity. The stated ambition is to cover somewhere between 500 and 1,000 astronomical units within roughly 50 years of launch, 5 to 10 times the distance either current spacecraft has managed across nearly 5 decades of continuous travel. Achieving that would demand a cruising speed somewhere in the range of 80,000 to 160,000 miles per hour, roughly double the velocity these older spacecraft currently maintain or more, likely requiring either a considerably more powerful launch vehicle, a close gravitational slingshot maneuver past the sun itself, paired with some form of advanced thermal propulsion, or some other propulsion breakthrough not yet fully mature. Among the priority science objectives, a far more detailed look at both the compressed nose and the long trailing tail of the heliosphere. One existing spacecraft crossed relatively near the nose, the other crossed closer to the flank, but neither has ever sampled the tail directly, so its true extent and internal structure remain almost entirely unknown. A proper interstellar probe could also survey the outer heliosphere far more systematically than the existing point measurements allow. mapping how conditions actually vary across both distance and direction, rather than relying on just two narrow trajectories. Pushing out to 500 or 1,000 astronomical units would also offer a real chance to determine whether the interstellar medium properties already measured by the two existing spacecraft are broadly typical of the wider local neighborhood, or whether they vary considerably depending on direction and distance. The mission might also finally locate that theorized bow shock out in the interstellar medium, somewhere in the neighborhood of 140 to 230 astronomical units according to existing models. Though given how badly those same models missed the heliopause's actual location, the bow shock, if it exists at all in any clean, recognizable form, could realistically be located almost anywhere. Either confirming it or ruling it out entirely would carry real scientific value. Such a spacecraft would likely carry more advanced particle detectors for characterizing galactic cosmic rays in far greater detail, sensitive magnetometers to better map the structure of the local galactic magnetic field, plasma wave instruments tuned to catch turbulence and shock activity rippling through the interstellar medium, and conceivably even a camera capable of capturing a genuine portrait of the entire solar system from well outside its boundary. An updated, far more detailed version of that single faint pixel captured decades earlier. But the mission, as things currently stand, remains decades away from actually launching. Engineering and design work continues. Funding has yet to materialize, and even under an optimistic timeline, launch likely wouldn't happen before sometime in the 2030s, meaning the spacecraft wouldn't even approach the 500 astronomical units mark until sometime around the 2080s at the earliest. Most of the scientists currently doing the early design work probably won't personally live to see the mission's core scientific results come back. That's simply the nature of exploration operating on this particular scale. These two original spacecraft launched at a moment when many of the researchers now analyzing their data hadn't even been born yet. The engineers currently maintaining the ground stations that keep in touch with them weren't alive when the spacecraft were first assembled. Whoever eventually receives the very last transmission either spacecraft ever sends is, quite possibly, sitting in an elementary school classroom somewhere right now with no idea that distinction awaits them decades down the line. Genuine scientific progress on this kind of timescale demands institutional patience, stretched across multiple generations, a willingness to commit to projects whose ultimate conclusions, the people starting them, will likely never personally witness. That pattern isn't unique to spaceflight either. Historical expeditions into unmapped territory routinely took generations to actually result in lasting settlement. The first voyage to circumnavigate the globe was completed only because the expedition continued on without the original commander, who died partway through. Humans landed on the moon more than 50 years ago, and, as of today, still haven't returned. Progress along these frontiers rarely moves in a straight line. It comes in uneven bursts, periods of rapid breakthrough followed by long stretches of consolidation, sometimes even outright retreat. These two spacecraft represent a particular convergence of circumstances: available funding, sufficiently mature technology, a rare and favorable planetary alignment, and enough institutional will to attempt something genuinely unprecedented, all lining up at once. That same convergence might happen again. The proposed interstellar probe might eventually fly. Humanity might send additional spacecraft out into true interstellar space down the road. Or it might not. At least, not for a very long while. These two original machines might end up remaining, for decades or even centuries to come, the only spacecraft that have ever directly sampled conditions beyond the heliopause. Either way, what they've already found stands on its own, permanently. The measurements exist, carefully archived. The images are stored and safely backed up. The resulting knowledge has already been folded into humanity's broader scientific understanding, regardless of whether any successor mission ever actually launches. One more thread worth pulling on before we wrap up. None of this stays confined to our own solar system. Astronomers have spent the years since these crossings turning radio telescopes and X-ray observatories toward other nearby stars, hunting for evidence of similar bubbles, sometimes called astrospheres, carved out by other suns, pushing their own stellar winds into the surrounding interstellar gas. A handful of nearby stars show faint, indirect signatures consistent with exactly this kind of structure. A star moving through the galaxy, compressing a bow-shaped boundary ahead of it, trailing a long, faint wake behind. None of those distant astrospheres can be measured directly the way ours now has been. No spacecraft is ever going to fly to another star's boundary and stick instruments into it within any time scale that matters to us. But having one confirmed, directly sampled example sitting in our own backyard gives researchers something invaluable: a calibration point. When a model of some distant star's astrosphere produces a prediction, researchers can now ask how well that same modeling approach would have done predicting our own heliosphere. And the honest answer, given everything we've just walked through, is not particularly well. That's a humbling but genuinely useful piece of information to carry into the study of other systems. A built-in reminder that whatever number a simulation spits out for some distant star's bubble boundary, the real boundary sitting behind that simulation may well sit billions of miles farther out or considerably closer in, shaped in ways the model never anticipated, the same way ours turned out to be. It also reframes how researchers think about habitability and radiation exposure on planets orbiting other stars entirely. A planet's home star sweeps out its own bubble of relative shelter from galactic cosmic rays, just as our own sun does for us. And the size, shape, and stability of that bubble plausibly factors into how much high-energy radiation reaches any given planet's surface over geological time, with potential downstream effects on atmospheric chemistry and even the long-term prospects for surface life. Before these two spacecraft actually measured our own boundary directly, that whole line of reasoning rested entirely on theoretical extrapolation. Now it rests on at least one confirmed ground truth example, however imperfectly it generalizes to stars very different from our own. So tonight we walk through everything two aging spacecraft revealed once they finally reached the true edge of the solar system. Two machines launched in 1977, carrying computers with less processing power than a basic pocket calculator, originally engineered to last only 5 years. And yet, here they are, nearly 50 years later, still technically functioning. They visited Jupiter first and discovered active volcanism erupting on one of its moons, the first confirmed evidence of volcanic activity found anywhere beyond Earth. They studied another moon's cracked, youthful ice surface and found tantalizing hints of a hidden ocean lurking beneath it. They discovered Jupiter possesses its own faint ring system, something nobody had confirmed before. They moved on to Saturn and revealed that its rings, long assumed to be a handful of broad, simple bands, actually consist of thousands upon thousands of individual ringlets. They studied Titan's surprisingly thick, organic-rich atmosphere in detail. They mapped magnetic fields and radiation environments at both giant planets along the way. One of the two spacecraft then pressed onward to Uranus and Neptune, becoming, and remaining to this day, the only spacecraft ever to visit either distant ice giant. It photographed the strange, shattered-looking terrain of a small moon orbiting Uranus. It discovered a colossal dark storm churning in Neptune's atmosphere and measured wind speeds exceeding 1,300 miles per hour, the fastest ever recorded anywhere in the solar system. It studied active nitrogen geysers erupting on one of the coldest moon surfaces ever measured. And then both spacecraft kept right on going, well past the planets entirely, out toward the true edge of the solar system. They crossed the termination shock, the point where the relentless outward rush of the solar wind finally slows from supersonic to subsonic speed. They pushed through the Helios heath, the turbulent transitional region beyond it. They stumbled across the entirely unanticipated magnetic highway, a structure no model had ever predicted could exist. One spacecraft crossed the heliopause itself in August of 2012, at a distance of 121 astronomical units, far beyond anything the models had promised. Its twin crossed in November of 2018 at 119 astronomical units. Together they revealed that the heliopause sits billions of miles farther out than anyone had calculated, that its overall shape is lopsided and asymmetric rather than the simple, tidy bubble everyone expected, that the actual transition across the boundary is messy, prolonged, and riddled with unexpected structure rather than the clean handoff the models promised. They directly measured the interstellar medium for the very first time in human history. Density, temperature, pressure, all turning out slightly different from prediction. They detected shock waves triggered by solar storms continuing to ripple outward through interstellar space itself, long after leaving the heliosphere proper behind. They measured the orientation of the galactic magnetic field and found it behaving in ways nobody had anticipated. They mapped the directional pattern of incoming cosmic rays and uncovered real structure hiding within the local interstellar environment. 6 major lines of discovery, and in every single case, the original prediction missed the mark in some meaningful way. Not catastrophically wrong. The underlying physics held up fine. The basic conceptual picture survived, largely intact. But every specific number, every quantitative forecast, came back wrong to one degree or another. That's precisely what genuine exploration does. It takes whatever understanding we've built and tests it directly against reality. And reality has an unfailing habit of turning out more intricate than any theory built in advance. These 2 spacecraft handed us a lasting lesson in humility. We thought we had a solid handle on where and how the solar system ends. We built increasingly sophisticated computer simulations. We ran those models for years, refining them as new data came in. We made confident, specific predictions about exactly where the boundary would sit, what shape it would take, how cleanly the transition would unfold. We drew textbook diagrams depicting a neat, well-behaved, spherical boundary. We published detailed calculations specifying the precise distance at which a spacecraft should expect to cross it. And then 2 actual spacecraft went out there, took real measurements, and revealed that nearly every specific detail we thought we understood turned out to be at least somewhat wrong. Not wrong about the fundamental physics, to be clear. The basic mechanism still holds. The solar wind genuinely does collide with the surrounding interstellar medium. A real boundary genuinely does form where their respective pressures balance out. Cosmic ray intensity genuinely does increase once you cross beyond that boundary. But every specific, quantitative prediction, the exact distance, the precise shape, the expected duration of the transition, missed in some meaningful way. The distance was off by billions of miles. The shape turned out lopsided, rather than the predicted symmetric sphere. The transition stretched across years, rather than the predicted weeks. The magnetic highway wasn't anticipated by anyone, at any point, in any model. The interstellar medium's actual measured properties diverged from earlier estimates. The galactic magnetic field's orientation caught everyone by surprise. The directional pattern of cosmic rays didn't match what anybody expected going in. That's how genuine scientific progress actually tends to unfold in practice. Rarely the smooth, linear march toward confirmed certainty that textbooks sometimes make it look like in hindsight, and more often, a genuinely messy, iterative cycle. Build the best model the available data supports. Generate a prediction from that model. Go out and actually test the prediction directly. Discover where reality diverges from expectation, and use that divergence to refine the model further before generating the next round of predictions to test all over again. These 2 spacecraft offer about as clean an example of that whole cycle as you're likely to find anywhere in the history of science. The researchers who built those original models weren't careless or incompetent in any sense. They worked from solid physics and the best data available at the time. The universe simply turned out to hold more complexity than any model built in advance could fully anticipate. Factors nobody had properly accounted for. Properties of the interstellar medium that had been estimated incorrectly. Dynamic behaviors at the boundary nobody had seriously considered. Phenomena like the magnetic highway that nothing in the existing theoretical framework had even hinted might be possible. And that's perfectly fine. Genuinely fine. Those mistaken early predictions weren't failures in any meaningful sense. They were opportunities. Openings that allowed for real discovery. Chances to sharpen understanding and build sturdier models for whatever spacecraft comes next. These 2 machines are dying now. Slowly. Steadily. with no real way to stop the process. The plutonium fueling their power generators keeps decaying away on schedule, year after year, without fail. And the available power keeps dropping right alongside it. Instruments keep getting shut down, one after another, in a continuous effort to stretch out the remaining electricity for as long as possible. Heaters get switched off, leaving delicate components to freeze. Backup systems get activated as primary ones finally give out. Mission engineers spend their days performing an ongoing, unglamorous triage, deciding moment by moment what's worth preserving and what has to be sacrificed. Sometime around 2030, perhaps stretching out to 2032 at the very latest, there simply won't be enough power left to keep going. The transmitters will fall permanently silent. The final signal will fade quietly into the background noise of deep space. And the ground stations, listening for it, will no longer hear anything at all coming from that particular point in the sky. But the spacecraft themselves will keep traveling regardless, at roughly 38,000 miles per hour, forever, with nothing out there to slow them down. No friction in the vacuum of space, nothing capable of bringing either one to a stop. They'll simply keep drifting outward, year after year, decade after decade, century after century, passing through the very same interstellar medium they spent years measuring, sailing through shock waves triggered by distant solar storms and stellar outbursts they help first reveal, moving through regions of varying density and varying magnetic field structure that will go entirely unrecorded from that point forward, since their instruments will have long since gone dark, unrecorded, but no less real for going unmeasured, still happening, regardless of whether anything remains to observe it. And all the while, they'll keep carrying their golden records along with them, the recorded sounds and images and music of an entire planet, drifting outward through the emptiness, Baroque counterpoint and orchestral symphonies, and early rock and roll, greetings spoken in 55 different languages that no living ear will ever actually hear, images of Earth and its people and its solar system that no eye will ever actually see, barring some near infinitesimal stroke of chance. Roughly 40,000 years from now, both spacecraft will make their respective closest approaches to other stars, still more than a light year away even at that nearest point. Nowhere close enough to count as genuinely arriving anywhere, just two small objects passing quietly through the vast emptiness separating one star system from another. The odds anyone or anything will ever notice either spacecraft passing by remain close enough to zero to dismiss outright. Space is too immense. The galaxy holds too many hundreds of billions of stars, and these two small, cold, dark objects are nowhere near aimed at any particular destination in the first place. And yet, they'll persist out there regardless for millions of years, very likely for billions, quite possibly, right up until the sun itself eventually swells, fades, and ultimately burns out as a white dwarf. Quite possibly even longer than that, long enough to witness changes in the galaxy's own structure that remain almost impossible for us to properly picture today. Even if no one and nothing out there ever encounters either spacecraft, even if neither one ever crosses paths with any other civilization in the entire history of the universe, even if both eventually meet their end through some chance collision or simply succumb to the slow accumulation of radiation damage across geological timescales, they will already have served their purpose entirely. They explored the outer planets and fundamentally rewrote our understanding of them. They crossed the boundary marking the edge of the solar system and measured true interstellar space directly for the very first time in human history. They demonstrated, repeatedly and conclusively, that our most careful models were missing something important, that the universe holds more genuine complexity than any theory built purely in advance can ever fully capture. They proved beyond any doubt that human engineering really can produce machines capable of surviving and functioning in one of the harshest environments imaginable. Machines that go on operating for decades longer than anyone ever expected. Machines capable of venturing into the genuinely unknown and successfully sending knowledge back home. And the knowledge they returned, the actual data, the specific measurements, the carefully recorded surprises, all of that is permanent now. Nothing can take it away. Whatever interstellar probe eventually does get built, if one ever does, will lean directly on what these two original spacecraft already discovered to help plan its own trajectory and design its own instruments. Future textbooks will keep citing these findings about the heliosphere and interstellar space for as long as anyone keeps studying the subject. Future scientists will keep returning to this same archived data for decades still to come, very likely uncovering fresh insights buried in there that nobody has thought to look for yet. The raw measurements sit safely preserved in NASA's archives. The images remain stored and thoroughly backed up. The accumulated knowledge has already been woven permanently into the fabric of humanity's broader scientific understanding. These two machines showed us exactly where the edge of the solar system actually sits. And in the process, they showed us that even at that edge, even at a boundary, scientists genuinely believed they understood reasonably well going in. Reality turns out to be stranger, more dynamic, and considerably more interesting than anyone had managed to predict. They showed us that real exploration isn't really about confirming what you already believe. It's about uncovering what you don't yet know, about finding the surprises, waiting just past the limits of current understanding, about learning, again and again, that the universe consistently runs more complex, more fascinating, and more genuinely mysterious than even our very best theories ever managed to suggest. 2. Spacecraft, built using technology that predates the personal computer, still drifting outward after nearly 50 straight years, still teaching us new things, still managing to surprise us right up until the day their transmitters finally fall silent for good, and they slip permanently into the dark, carrying their quiet message outward toward the stars, a message from a species that, at least once, dared to look outward, dared to send a small piece of itself past the edge of everything familiar, and dared to ask what might be waiting out there, only to find an answer, stranger and considerably more wonderful than anyone had ever dared to predict in advance. If you made it this far, thank you for sticking with the whole story. Space exploration rarely moves at the pace of a headline. It moves at the pace of slow, patient data collection across decades, with the real payoff often arriving long after the initial launch has faded from public memory. These two machines are a reminder that the universe rewards that kind of patience, that the most interesting discoveries are often the ones nobody planned for, found by instruments doing exactly what they were built to do, just for far longer and far farther from home than anyone ever expected. Somewhere out past 150 astronomical units right now, two small machines built half a century ago are still quietly doing science, still sending back whispers of data across billions of miles, still proving that the edge of what we think we know is rarely the edge of what's actually out there.